So today we are gonna be making progress in our calculus series. In the previous video, I showed you how the derivative of sin x is cosine of x, and then now I can show you the derivatives of cosine of x and show you how it turns to minus sin of x, like derivative of tan x, how it turns to square x. But I think like just spoon feeding you all the formulas what the proper way of teaching, at least in my opinion. I think you should find out those yourself by your own calculations. Today, what I'm gonna be teaching you guys is exponential functions and logarithmic functions and how we find their difference. First of all, let me write down the title here. ddx of exponential and logarithmic function. Okay. Before that, you'll have to understand that what is E. E is Euler's or in American English called as Euler's constant. Whose value is 2.718. This decimal just keeps on going forever, but the rough value of it converts us to 2.718. Now, what does this come from? E is nothing but the limit of as h. In this case, it's going to be n as n approaches zero of 1 plus 1 over n whole to the power n, or this is another form, E equals limit as in this case it would be as n approaches infinity, my bad, and here too n would tend to infinity, but this time it looks something like this: 1 plus n whole to the power 1 over n. Okay, let's actually move the camera this way. Okay, so, and this is really crucial when we have to find out the derivatives of exponential functions and logarithmic functions as well. We find out how. So in order to understand this, you have to understand what is natural logarithm. Okay, then it's called logarithm of naturalist. It's a Roman word, but in English it's called natural logarithm, and it's written like this: ln. This is nothing but ln of x is nothing but log of x, where the base of the log is e. And what is e? 2.718 dotted. Natural logarithm is just a logarithm with the base e in this specific number. Okay. Now we have to understand about few specific properties of the number e. First of all, when you raise e by a variable and get a function of that and try to find out the differentiation of that function with respect to that variable, it has e with that variable, which means ddx of e to the power x is also e to the power x. And how does that happen? Let me show you. ddx of to the power x with the first rule, as limit h approaches 0 of e to the power x plus h, e to the x plus h minus e to the x divided by h. I can write this down as e to the x times e to the h minus e to the x whole divided by h. I can factor out e and e to the power x and take it outside of the limit, because e to the power x itself does not depend on the value of h. So this would be like e to the power x times limit as h approaches 0 of e to the power h minus 1 whole divided by h. Now you can get a calculator and find the value of this, where e is the specific number 2.718. Actually most calculators probably have a number called e itself, e written on them, and you can raise e by a very small number and then subtract 1 from it and then divide the whole thing by that very same number that you raised e by, and you will get 1. This would converge to 1. So this would just leave us with e to the x. So this means the derivatives of e to the power x is also e to the power x. This is very crucial. Now we will understand another thing, that what is the derivative of e to the power constant times x with respect to x. This time the function we have is just not e to the power x. The function itself has e to the power x in it, but alongside with x, the function also has a constant that the number is being raised to, and actually e is being raised to the product of the constant and the variable x. Okay, so how would this look like? Again with the first rule, as limit of h approaches 0, this would just be e to the power a times x plus h minus e to the x whole divided by h again. I can write this down as limit of h tends to 0, e to the ax times, sorry, here actually we have got the x times e to the h minus e to the ax whole thing divided by h. Now keep in mind, some people might think that the derivatives of e to the power ax would also be e to the power x, but that would not be the case. That would have been the case if what we are finding out the derivatives with respect to was ax. But since we are trying to find out what is the rate of change of this function with respect to x, then that would not be the case. Let me show it then. You can also factor out e to the power ax from here. Because e to the power ax does not indeed depend on h here. So this would just look like e to the power ax, and as limit h approaches 0, this would be e to the power h minus 1 over h. Wait a minute. This also turn into 1. I'm making a crucial mistake here. I just forgot that here a was being multiplied with both x and h. So this won't be e to the power ax times e to the power h. This would be e to the power x times e to the power h. So this would be e to the power ah. And when I multiply this with an a and divide by a, that will just remain the same, because a and a can cancel out each other and this both will remain the same. Now I can bring out this a in front. This would be e to the power ax times a of limit h approaches 0 of e to the power ah minus 1 over over ah. Here too the value of ah would approach 0 because the value of h is approaching 0. There is a constant is being multiplied with something very small, so the overall product also be very small. You can also go to a calculator and find this out. This would also converge to 1, which would leave us with a times a to the power, a times e to the power ax. Okay, so you can see that e to the power ax is e to the power ax is a times a to the power a times e to the power x. Now, if you're done understanding all that, if you're done, and comprehend all that, now we'll find out what the differentiation of exponential function looks like. Let me show it to you. Let's say we have a function here, exponential function f of x, which equals a to the x. And if we were told to find out the derivative of this function, this would be ddx of a to the power x. Now, if the constant was something that the variable is first thing is to like x to the power a, then we know by the power rule of polynomial functions that we would have gotten a times x to the power a minus h. But since this time the constant is being raised to the variable, things would be very different. We can write down a to the power x as e to the power ln of a to the power x. Why, you ask? It's because of this ln of a to the power x. Let's know what logarithms are, right? Logarithms basically ask that what number their base should be raised to get the number that the logarithm function is being applied to. This time this is a logarithm function, and then it's nothing but a logarithm function with the base e. This asks a question that what power should I raise the number e to get a to the x. This number is that ln of a to the power x. Okay, and since we are raising e by that number, we should get a to the power x. We are raising e by this number. We are raising e by a number that when you raise e to that number, we get a to the power x, and we are raising e to the power a with that number, so we should get a to the power x. This means we can write a to the power x as e to the power ln of a to the power x. Okay, so if we find out the derivative of e to the power ln of a to the power x, we will find out what the derivative of a to the power x is, right? Because these two functions are the same. When you plot a graph of this either of this function, they would their representatives would be identical to each other. So trying to find a slope in that curve of a particular point in both graphs would be the same thing. So, and from the previous section of this video, we found out that when e was was being raised to a constant times a variable, actually it's a constant because e to the power x is being raised to a constant and a constant a product of a constant and a variable. What does that look like? This is gonna be ln of e to the power x. Since you know that ddx of e to the ax was a times e to the x. Okay, so this would just become ln of a to the power x times e to the power this would just become ln of a times e to the power e to the power ln of e to the power x. Okay, I don't think there should be any problem with answering anything here. So they found out what the derivatives of an exponential function looks like. It looks like something like this. Let's say we have a constant a which is being raised to the variable x, and we want to find out what the derivative of that looks like. It will be ln of a times e to the power ln of a to the power x. Okay. Now, what does the derivatives of a logarithmic function looks like? First of all, we will find out what the derivative of a logarithmic function with the base e, which is natural logarithm ln function of x equals ln x. Then that function's rate of change ddx of ln x. What would that be? With the first rule again, this would be limit of h tends to 0 of ln of x plus h minus ln of x divided by h. Okay. Then limit of h tends to 0. Now, if you guys have probably studied logarithm, you understand that you probably remember that there is a logarithmic property that says that the subtraction of two logs just equals the log of the log of basically the ratio of the two numbers that the logarithmic functions were originally being. What does that mean is that this would just become ln of x plus h over x, this is not t, x over h. This would become limit of h tends to 0 what would this become? I can write it down like this would be x to the power x plus x to x to the x by x by plus h by x. Okay, and this would just become 1 plus h by x. This would just become 1 plus h over x instead of the natural logarithm function whole divided by h. Okay. Now, what would have to happen after this? I can write it down like x over h of as ln of 1 plus h over x times 1 by x. How you ask? Because what did I just do here? I just multiplied this whole thing with x and divided this whole thing by x. So this take this x and this x to just cancel out each other and will just leave us with what we had earlier, ln of 1 plus h by x whole by h. Okay, and since this 1 over x does not depend on h, we can bring it out in front. So let me write it down here. We can bring it out in front. It will look like 1 by x times limit of h tends to 0. Now, there is another rule of logarithm that says that if your logarithmic function is being multiplied with something, you can, what you can do is you can take the number and basically raise the number that logarithm function is being applied. So for this would just become ln of 1 plus h over x raised to x by h. This is logarithmic property. You need to have proper understanding of logarithm to comprehend what is going on here. Now, if we look at this thing, 1 plus h over x raised by x over h, what does it look like? I told you guys E is as limit limit n approaches 0. This is 1 plus 1 over n, or this 1 plus n raised by 1 over n. So let h by x equals n. So x by h is what? Is 1 over n. If h by x is n, then x by h should be 1 over n. So this just looks like this, doesn't it? We have a function here, 1 plus h, 1 plus a number, and we are raising that whole thing with the reciprocal of that number. Just like here, this is the definition of E. So this would just, and since and you will ask that, sorry, actually I made a mistake here, n would tend to infinity, and you would ask that here h is approaching 0, this two things don't look the same. Here if h in this particular context, here if h approaches 0, this number actually doesn't matter actually. Actually, I think that it does. Here, if h goes closer and closer to 0, since we are taking a very small number and then dividing it, and then dividing it by a moderately sized number, that would just result in infinity. I mean, we know that we can get to the absolute point where infinity is, but as I told you guys in the previous videos, that these things are all based on a few very good assumptions. So here n goes to infinity, and over here to h or x, they don't go to infinity, but this thing h over x does go to infinity. And here if n goes to infinity, then reciprocal of that, 1 by infinity goes to 0, 1 by n goes to 0. And if h by x here goes to 0, then its reciprocal x by h, that would just also approach 0, because that would I'm making a mistake here. Yeah, I think a better way to write this down would be 1 plus 1 over n, this whole thing raised by, it's the same thing, it's the same thing. Now you can say that as this n goes to infinity, this 1 over n thing goes to 0. Here as h goes to 0, this whole thing goes to 0. Here n goes to infinity, so this whole thing goes to infinity. It's just a sign of it. And here as h goes to 0, this x by h goes to infinity. So now these two things look the same. Now what would this become? This would become E. So this would just be we don't need to try to limit anymore. This would just become ln of E. Now what is ln? Ln is natural logarithm. This is a logarithm with a base E in it. Now we know that there is a logarithm function that log a with the base a just becomes 1, because this asks a question like what number should we raise a by to get a, and that could be 1, because when we raise a to 1, that just becomes 1 a. So this also asks that what number e should be raised to give us e, and that will just become 1. Okay, this would just become 1. So derivatives of natural logarithmic function is 1 over x. Now I am giving you tasks to find out what the derivatives of logarithm function with a general logarithm function with any kind of base would look like. It's your job to find out that. And if you can do that, I'll definitely explain how that looks like. So that's it for today, guys. See you tomorrow and keep learning.